Hello, and welcome to Space for Sleep. There was a time when there were no stars. There were no galaxies, no planets, and no neutral atoms. There was not yet darkness in the familiar astronomical sense of empty space between stars, because stars in transparent space had not formed. The region that would become our observable universe was filled with a hot, dense mixture of radiation and particles. Space was expanding. The temperature was falling. And within that simple beginning lay the physical conditions from which every later structure would emerge. We call this early history the Big Bang. The name can be misleading. It suggests a detonation, an object exploding at one location and throwing material outward into a surrounding emptiness. That is not what the standard cosmological model describes. The Big Bang was not an explosion in space. The term refers to the universe's hot, dense early phase and to the expansion and cooling that followed. In general relativity, the average distances between unbound regions grow as the geometry evolves. Matter is not simply flying outward from one central point into a surrounding emptiness. Nor does the Big Bang model, by itself, prove that the universe emerged from absolute nothingness. It describes the universe with great confidence back to a very early hot, dense state. When the equations are pushed farther into the past, they eventually reach conditions where our tested theories are no longer sufficient. Whether that boundary was the absolute beginning of time, a transition from an earlier phase, a quantum event without an ordinary before, or something not yet imagined remains unknown. That distinction matters. Science is strongest when it separates what observation has established from what theory suggests and from what remains open. What observation has established is remarkable enough. The universe is expanding. It was once much hotter and denser. Light nuclei formed during its first minutes. A nearly perfect bath of thermal radiation still fills all of space, carrying an image of the universe when it was only about 380,000 years old. Tiny variations in that ancient light matched the seeds from which galaxies and clusters later grew. The age inferred within the standard cosmological model is about 13.8 billion years. This number is not obtained from one clock. It emerges from a network of measurements. The present expansion rate, the geometry and composition of the universe, the pattern of the cosmic microwave background, the clustering of galaxies, and the ages of the oldest stars. Different methods do not agree perfectly in every detail, but they agree that the cosmos has a finite observable history extending back almost 14 billion years. The phrase observable history is important. The observable universe is the region from which signals have had time to reach us. It may be only a small part of a much larger universe. The entire universe may be finite or infinite. Current observations tell us that space is very close to geometrically flat across the region we can measure, but they do not reveal the total size or global shape with certainty. If space is infinite today, it may also have been infinite at earlier times. Expansion would then mean that distances between neighboring regions were smaller, not that an infinite universe was compressed into one ordinary point. If space is finite and unbounded, it can expand without having an edge and without expanding into an external room. In either case, the Big Bang did not occur at one privileged center. Every sufficiently distant galaxy sees other distant galaxies receding in the same broad pattern. An image can help, provided we do not take it too literally. Imagine points painted on the surface of a balloon as the balloon inflates. Every point sees the others move away. No point on the surface is the center of the expansion within that surface. The balloon analogy adds an external dimension that the real universe may not have, so it is imperfect. Its value is simply to show how every location can participate in expansion without one location being the origin. Another image is a loaf of raisin bread rising in an oven. As the dough expands, The average distance between raisins increases. The raisins are not necessarily racing through the dough under their own power. The material between them is stretching. Again, the analogy has boundaries and an outside, while the universe need not. But it captures the difference between motion through space and the growth of distances caused by expanding space. At small scales, expansion does not pull everything apart. Electromagnetic forces hold atoms together. Gravity holds planets, stars, galaxies, and many galaxy groups together. The solar system is not expanding with the universe. The Milky Way is not being stretched internally by the Hubble flow. Cosmic expansion becomes dominant only across sufficiently large distances where local binding is weak compared with the overall evolution of spacetime. The title Big Bang was introduced by the British astronomer Fred Hoyle during a BBC radio broadcast in 1949. Hoyle supported a competing model called the steady-state theory, in which the universe expanded but maintained a constant average density through the continuous creation of matter. The phrase Big Bang was memorable, whether or not it was intended as ridicule, and it remained after the steady-state model lost support. The steady-state universe was elegant. It had no special beginning and looked broadly similar at every time as well as every place. But nature did not cooperate. Distant galaxies and radio sources showed that the universe had changed over cosmic history. The abundance of light elements pointed to a hot nuclear phase. Most decisively, the cosmic microwave background revealed thermal radiation left from a much hotter past. Tonight, we will follow that past gently and carefully. We will begin with galaxies whose light is stretched by expansion. We will listen to the microwave afterglow that fills the sky. We will move through the first fractions of a second, while clearly marking the places where knowledge becomes speculation. We will watch quarks become protons and neutrons, nuclei form before atoms, and light finally travel freely. We will pass through the long dark interval before the first stars, and then into the growing cosmic web. We will also consider the unanswered questions. We do not know what produced the matter-antimatter imbalance. We do not know the identity of dark matter. We do not know whether inflation occurred in exactly the form most often described. We do not know whether the mathematical singularity of classical relativity corresponds to a physical beginning. And we do not know why the early universe possessed the unusual order that gave time its direction. The Big Bang is therefore not a finished story in which every page has been read. It is a well-tested framework surrounding several deep mysteries. Its beginning may have been energetic beyond imagination, but on the largest scales it was astonishingly smooth. The early universe did not begin as a chaotic spray of finished objects. It began almost uniform, with tiny differences in density. Those quiet irregularities were enough. Gravity slowly amplified them into stars, galaxies, clusters, and the immense filaments of the cosmic web. Everything complicated came later. The observational foundation for the Big Bang rests on several pillars, established by different kinds of measurement and joined by a common mathematical framework. The first is the expansion of the universe. The story began before anyone knew that the Milky Way was one galaxy among many. In 1912, Vesto Slipher at Lowell Observatory measured the spectrum of the object, then called the Andromeda Nebula. Spectral lines appear at characteristic wavelengths when atoms absorb or emit light. If those lines are shifted, the shift contains information about relative motion and, in a cosmological setting, about the stretching of space during the light's journey. Slipher found that Andromeda was blue-shifted and moving toward us. Over the following years, he measured many more spiral nebulae. Most were redshifted. The pattern was striking, although its meaning was not yet clear because astronomers were still debating whether spiral nebulae were nearby structures inside the Milky Way or distant island universes beyond it. Alexander Friedmann supplied an important theoretical step in 1922. He found dynamic solutions to Einstein's equations of general relativity. A universe filled with matter and radiation did not need to remain static. Its scale could change with time. It could expand or contract. Georges Lemaitre reached a similar conclusion independently. In 1927, he combined a relativistic expanding universe solution with the available redshift and distance estimates and derived a relation between recession and distance. He even estimated the proportionality constant. His paper appeared in French in a journal that attracted limited international attention, but the essential idea was already present. Observations and relativity were pointing toward an expanding cosmos. Edwin Hubble's work supplied the decisive observational demonstration. Using the 100-inch Hooker telescope at Mount Wilson, Hubble identified Cepheid variable stars in the Andromeda Galaxy and other spiral systems. Henrietta Swan Leavitt had previously discovered that the pulsation period of a Cepheid is related to its intrinsic brightness. By comparing intrinsic brightness with apparent brightness, astronomers can estimate distance. Those measurements established that the spiral nebulae were far outside the Milky Way. Hubble then assembled galaxy distances and paired them with radial velocities, many ultimately based on Slipher's spectra and later work by Milton Humason. In 1929, he published a graph showing that, despite considerable scatter, more distant galaxies generally had larger recession velocities. The relationship is now called the Hubble-Lemaitre law. At distances where local motions are small compared with the cosmic expansion, recession speed is approximately proportional to distance. The proportionality factor is the Hubble parameter. Its value changes through cosmic history, so the value measured today is called the Hubble constant. The law does not mean that Earth occupies the center of a conventional explosion. An observer in a sufficiently distant galaxy would infer the same large-scale expansion. Every region sees remote regions receding, just as every raisin in rising dough sees other raisins move away. The redshift also deserves care. For nearby galaxies, it can be treated approximately like a Doppler shift caused by motion. Across cosmological distances, a deeper description is needed. A light wave travels while the scale of the universe changes. The wavelength is stretched along with the expanding space through which it moves. A photon emitted when the universe was smaller arrives with a longer wavelength and lower energy. The cosmological redshift is usually written as a number called z. A redshift of 1 means that the universe has expanded by a factor of 2 since the light was emitted. A redshift of 6 means the scale factor has increased by a factor of 7. The relation between redshift and look-back time is not a simple linear conversion, because the expansion rate has changed as radiation, matter, and dark energy dominated at different eras. Nearby galaxies do not all follow the smooth flow exactly. Gravity gives them peculiar velocities relative to the expansion. The Andromeda Galaxy is approaching the Milky Way because the two belong to the same gravitationally bound local group. Galaxies and clusters orbit within the cluster's potential. Only when observations average over large enough scales does the Hubble-Lemaitre pattern become clear. The modern Hubble diagram extends far beyond Hubble's original sample. Astronomers use several overlapping methods to measure distance. Parallax provides a geometric foundation for nearby stars. Cepheids and other variable stars extend the ladder to nearby galaxies. Type 1a supernovae can be seen across billions of light years. Baryon acoustic oscillations provide a standard ruler rather than a standard candle. Gravitational wave events can act as standard sirens. These methods allow astronomers to reconstruct not only that the universe expands, but how the rate of expansion has changed. In the late 1990s, observations of distant Type 1a supernovae revealed that expansion is accelerating today. The supernovae appeared dimmer, and therefore farther away, than expected in a universe slowing under the gravity of matter alone. Within the Standard Model, the acceleration is attributed to dark energy, represented in its simplest form by a cosmological constant. The cosmological constant has an unusual history. Einstein introduced it while seeking a static cosmological model. He later abandoned that static construction after expansion became established. The often repeated story that he called the constant his greatest blunder is not securely documented in his own writings and should be treated cautiously. More importantly, a mathematically similar term returned decades later as the simplest description of accelerated expansion. The present expansion rate remains an active puzzle. Measurements that infer it from the early universe, especially the cosmic microwave background interpreted within the standard cosmological model, give a value near 67 kilometers per second per megaparsec. Several late universe distance ladder measurements give a higher value, near the low 70s. This difference is called the Hubble tension. It may reflect unrecognized systematic effects in one or more measurements. It may indicate that the Standard Model needs an additional ingredient between the early and late universe. Or the final resolution may involve several smaller changes rather than one dramatic discovery. The tension does not cast doubt on expansion itself. The expansion is observed through many independent methods. The uncertainty concerns the precise present rate and the model used to connect early and late measurements. Tracing expansion backward does not require us to imagine every galaxy returning to one ordinary point. Galaxies did not exist in the early phases. The matter that later formed them was distributed through a much hotter and smoother universe. As the scale factor decreases toward the past, average density and temperature rise. The evidence therefore leads to a hot, dense early state. That conclusion is stronger than a claim based on expansion alone because the other pillars show exactly the relics such a hot state should leave behind. The second pillar is the cosmic microwave background, the oldest electromagnetic light we can observe directly. Its existence follows naturally from a hot early universe. If matter and radiation once formed a dense thermal plasma, the universe should still contain the photons from that plasma. Expansion would stretch their wavelengths and reduce their temperature, but it would not simply erase them. In the 1940s, Ralph Alpher, Robert Herman, and George Gamow developed calculations of element formation in a hot early cosmos. Alpher and Herman recognized that relic radiation should survive and estimated that it would now have a temperature of only a few degrees above absolute zero. The prediction received less attention than it deserved and was not immediately followed by a successful search. The discovery arrived through an instrument built for another purpose. In the 1960s, Arno Penzias and Robert Wilson were using a large horn antenna at Bell Telephone Laboratories in New Jersey. They encountered a persistent microwave signal that remained after known sources of noise were removed. It came from every direction and did not follow the sky like an ordinary compact radio source. The antenna had been occupied by pigeons, and Penzias and Wilson cleaned what one paper politely called white dielectric material from the equipment. The detail became famous because it makes the discovery sound almost comic. But the essential work was meticulous calibration. The unwanted signal survived every reasonable attempt to explain it as equipment, atmosphere, nearby city, or known astronomical emission. At Princeton, Robert Dick, Jim Peebles, Peter Roll, and David Wilkinson were preparing an experiment to search for the relic radiation of a hot early universe. Communication between the groups revealed that the Bell Lab's noise was the signal the Princeton team hoped to find. In 1965, companion papers reported the measurement and its cosmological interpretation. The radiation is now called the cosmic microwave background, or CMB. It fills the sky because it fills the universe. It is not coming from a shell of material located at one special distance in the ordinary sense. In every direction, we see photons that last scattered when the early universe became transparent. The farther back we look, the closer we approach that surface of last scattering. The average temperature today is about 2.725 Kelvin. More important than the number is the shape of the spectrum. A hot body in thermal equilibrium emits a characteristic blackbody spectrum. Expansion lowers the temperature of a blackbody spectrum while preserving its form. The FIRAS instrument aboard the COBE satellite measured the CMB spectrum with extraordinary precision. It found one of the closest blackbody curves ever observed in nature, with deviations constrained to tiny levels. That near-perfect thermal shape is difficult to explain without an early period when photons and matter interacted so frequently that they reached thermal equilibrium. The CMB is often described as the afterglow of the Big Bang. The phrase is useful, but it can suggest that we are seeing light from the first instant. We are not. Ordinary photons could not travel freely through the much earlier plasma. The CMB was released about 380,000 years after the hot Big Bang phase began, when electrons became bound into neutral atoms and scattering became far less frequent. The mean microwave glow is almost uniform. If the motion of the solar system relative to the CMB is removed, the temperature differs from one direction to another by only about 1 part in 100,000. The largest visible pattern before that correction is a dipole. One side of the sky is slightly hotter and the opposite side slightly cooler. This is mainly caused by our motion through the CMB rest frame. Moving toward the radiation blue shifts it slightly. Moving away redshifts it. The dipole provides a cosmic reference frame defined by the average distribution of matter and radiation. It does not violate relativity. It simply identifies the frame in which the CMB is most nearly isotropic. After the dipole and foreground emission from the Milky Way are removed, tiny primordial fluctuations remain. COBE first detected these anisotropies on large angular scales. WMAP mapped them much more sharply. The European Space Agency's Planck mission measured temperature and polarization across a wide range of scales and produced the most detailed full sky map so far. The map is not a photograph of finished objects. Each warmer or cooler patch represents a slight difference in density, velocity, gravitational potential, or photon temperature in the early plasma. The variations are only tens of millionths of a Kelvin, yet they contain the blueprint of later structure. Gravity had already begun to act on regions that were slightly denser than average. Ordinary matter, however, was tightly coupled to photons. Compression increased radiation pressure, which pushed outward. The competition created acoustic waves in the photon-baryon plasma. Those waves produced a series of preferred scales. Some regions had completed one compression by the time photons decoupled. Others were caught in a rarefaction. Still others had undergone additional oscillations. When the CMB fluctuations are decomposed by angular scale, these patterns appear as acoustic peaks in a power spectrum. The positions, heights, and shapes of the peaks carry different information. The angular position of the first peak is sensitive to spatial geometry. The relative heights help determine the amount of ordinary baryonic matter and dark matter. The overall pattern constrains the age and expansion history. Damping on small scales records how photons diffused out of tiny fluctuations before last scattering. Gravitational lensing of the CMB by later structure reveals the integrated distribution of matter along the line of sight. Polarization adds another dimension. Thomson's scattering of radiation by free electrons can produce linear polarization when the incoming radiation has a quadrupole pattern. The CMB polarization is divided into patterns called E modes and B modes. E-mode polarization has been measured in detail and strengthens the standard cosmological picture. Large-scale E-modes contain information about reionization, because later free electrons scattered a small fraction of CMB photons after the first stars and galaxies ionized the intergalactic medium. B-modes can be produced by gravitational lensing, which twists part of the E-mode pattern. That lensing signal has been detected. A different B-mode pattern could be created by primordial gravitational waves generated during some forms of inflation. No definitive primordial B-mode detection has yet been made. Galactic dust emits polarized microwaves and must be separated with exceptional care. Within the standard 6-parameter cosmological model, Planck's final analysis found an age of about 13.8 billion years and a composition of roughly 5% ordinary matter, about 1/4 dark matter, and about 2/3 dark energy. The precise fractions depend on the model and data combination, but the broad result is robust. This means the familiar matter of atoms is a small part of the cosmic inventory. The CMB does not directly tell us what dark matter is or why dark energy exists. It measures their gravitational influence on expansion and acoustic structure. The CMB also constrains the initial fluctuations. Their spectrum is close to, but not exactly, scale invariant. Fluctuations on different scales have nearly the same statistical strength after an appropriate rescaling, with a slight tilt. This is consistent with many inflationary models, though not unique proof of inflation. The fluctuations are also close to Gaussian, meaning their statistical distribution resembles a bell curve and is largely described by two-point correlations. Searches for subtle non-Gaussian patterns test more complicated early universe physics. So far, the simplest initial conditions remain consistent with observation. There is another quiet fact hidden in the CMB. The photons vastly outnumber ordinary matter particles. For every baryon, there are roughly 1 billion background photons. The early universe was therefore radiation-rich, while the surviving excess of matter over antimatter was extremely small in relative terms. A map of the microwave sky appears mottled and still. In reality, it is a compressed record of several physical processes: quantum or primordial fluctuations, gravitational growth, acoustic motion, diffusion, recombination, reionization, and lensing across billions of years. No single image of the early universe contains more information. The third pillar is primordial nucleosynthesis, the formation of light nuclei during the first minutes. A hot early universe makes a precise promise. As temperature falls through the range where protons and neutrons can bind, nuclear reactions should produce a characteristic mixture, mostly hydrogen, a large and nearly universal fraction of helium-4, smaller amounts of deuterium and helium-3, and a trace of lithium-7. The exact yields depend on the density of ordinary matter, the expansion rate, measured nuclear reaction probabilities, the neutron lifetime, and the number of light particle species contributing to the early energy density. Once these inputs are specified, there is little freedom to adjust the outcome. The predicted helium-4 mass fraction is close to 1/4. Primordial deuterium is present at only a few atoms per 100,000 hydrogen atoms. Astronomers estimate the original helium abundance from low metallicity regions of ionized gas and the deuterium abundance from nearly pristine gas clouds seen in absorption against distant quasars. The observations agree impressively with the hot Big Bang calculation for deuterium and helium. Even more strikingly, the baryon density inferred from nucleosynthesis agrees with the value inferred hundreds of thousands of years later from the CMB acoustic peaks. The two methods rely on different physics and different observations. One uses nuclear reactions in the first minutes. The other uses sound waves and radiation at the time of last scattering. Their agreement links two distant eras of cosmic history. Lithium does not fit as neatly. The standard calculation predicts more primordial lithium-7 than is observed at the surfaces of many old, metal-poor stars. The difference may involve the way stars deplete or transport lithium, uncertainties in the astrophysical interpretation, or physics not included in the simplest calculation. The lithium problem remains open, but it does not erase the broader success of nucleosynthesis. The fourth pillar is the growth of cosmic structure. The microwave background shows a universe that was almost smooth. The modern universe is highly structured. Galaxies gather into groups and clusters. Clusters lie along filaments. Vast underdense regions form voids. On the largest scales, the arrangement resembles a web. A successful cosmology must connect these two views. It must begin with the small fluctuations measured in the CMB and produce the observed distribution of galaxies after billions of years of gravitational growth. Cold dark matter plays a central role. Because it does not remain coupled to photons in the same way ordinary matter does, dark matter can begin building gravitational potential wells before recombination. After neutral atoms form and radiation pressure releases its grip on baryons, ordinary matter falls into those wells. Computer simulations beginning with CMB-like initial fluctuations produce networks of halos, filaments, and voids resembling the observed cosmic web. The comparison is not made only by eye. Astronomers measure the statistical clustering of galaxies, gravitational lensing, the abundance of clusters, the distribution of neutral hydrogen, and the way structure changes with redshift. These measurements test the amount and behavior of matter and the expansion history that competes with gravitational growth. A fifth line of support comes from cosmic evolution itself. In a steady-state universe, the large-scale appearance of the cosmos should remain statistically similar at every epoch. But looking farther away means looking farther into the past, and the distant universe is visibly different. Quasars were more common at certain earlier times. Galaxies were generally smaller, more irregular, and more actively forming stars. Heavy elements were less abundant. The cosmic star formation rate rose, reached a broad maximum billions of years ago, and later declined. Radio source counts were among the early observations that challenged steady-state expectations. The CMB then delivered the decisive thermal relic. No simple steady-state model naturally produced a nearly perfect microwave blackbody together with primordial light element abundances and an evolving population of galaxies. The Big Bang framework also predicts that events in distant galaxies should appear time-dilated by cosmic expansion. A supernova light curve observed at redshift z should be stretched by a factor of 1 plus z. This time dilation is observed. It is another direct sign that redshift reflects an expanding spacetime rather than a gradual loss of photon energy through an unspecified tired light process. Tired light ideas once attempted to explain redshifts without expansion by proposing that photons lose energy during travel. Such mechanisms generally fail to reproduce the full collection of evidence. They do not naturally generate the observed time dilation, the blackbody microwave background, nucleosynthesis, acoustic peaks, and consistent distance relations at the same time. This is the strength of modern cosmology. The case does not rest on one graph, one telescope, or one theoretical preference. Expansion says the universe was denser in the past. The microwave background says it was once hot and opaque. Light element abundances say nuclear reactions occurred under those hot conditions. The cosmic web says small early fluctuations grew through gravity. The evolution of galaxies says the universe changes with time. Each line of evidence could contain uncertainty. Together, they form a tightly connected history that competing models have not matched with comparable economy and precision. The framework that best fits this evidence is called lambda cold dark matter, or lambda CDM. Lambda represents dark energy in the form of a cosmological constant. Cold dark matter supplies most of the gravitating matter. Ordinary baryonic matter provides atoms. Radiation and neutrinos dominate important early epochs. Lambda CDM is extremely successful, but it is not a final theory. It does not identify dark matter. It does not explain the microscopic nature of dark energy. It does not derive the initial fluctuation spectrum from a confirmed fundamental model. It contains tensions in some parameter measurements and possible hints of new behavior. A scientific model can be both incomplete and powerfully correct within its domain. Newtonian gravity remains useful even though general relativity is deeper. Thermodynamics describes heat without tracking every molecule. In the same way, the hot Big Bang model describes the thermal and expansion history of the universe, even though the ultimate origin of that history remains unknown. Before following the earliest timeline, it helps to arrange our confidence in layers. The first minutes are described by nuclear physics that can be tested in laboratories. The era of recombination is described by atomic physics, radiation transport, and gravity, all strongly constrained by observation. The quark-gluon plasma has partial experimental counterparts in heavy ion collisions. The electroweak era relies on the standard model at energies explored indirectly and, in part, directly by particle accelerators. Farther back, certainty fades. The standard model does not explain dark matter, the matter-antimatter imbalance, quantum gravity, or the origin of the initial conditions. Proposed grand unified phases and inflation may fit naturally into the story, but their microscopic details are not established. A timeline printed with an exact event at an exact tiny fraction of a second can therefore look more certain than the underlying science. Cosmic time itself is well defined within the large-scale homogeneous models used in cosmology. But when we extrapolate toward the Planck scale, around 10 to the minus 43 seconds in a simple classical estimate, quantum effects of gravity should become unavoidable. General relativity treats space-time as smooth. Quantum theory treats physical fields as fluctuating and probabilistic. We do not yet possess a tested theory combining the two in this regime. The Planck time is not an observed timestamp and not necessarily the first tick of a cosmic clock. It is a scale constructed from fundamental constants where our current description becomes unreliable. Statements about what happened earlier are proposals, not measurements. This gives the early universe story an unusual shape. The oldest light we directly observe comes from 380,000 years after the hot beginning. Yet physical theory, tested at later times and in laboratories, allows us to infer much earlier conditions. The farther we extrapolate, the more carefully the language must change from happened to may have happened. Near the Planck scale, classical equations predict enormous temperature and density. It is tempting to say that all forces were unified. Some theories propose such unification, but no confirmed theory tells us exactly what the degrees of freedom were. Space-time may have possessed a quantum structure unlike any familiar geometry. The ordinary distinction between space and time may have been only approximate, or a deeper theory may describe the regime in terms we do not yet have. As expansion continued, the universe entered conditions in which separate interactions became meaningful. The strong, weak, and electromagnetic interactions are described by quantum field theories, while gravity is described by general relativity. At sufficiently high energies, the electromagnetic and weak interactions merge into the electro-weak interaction, a feature supported by accelerator experiments. Whether the strong interaction joins them at a still higher energy is unknown. Grand unified theories predict such a merger and often introduce new particles or processes, including mechanisms that could help explain the matter-antimatter asymmetry. None has been confirmed. Between the Planck scale and the hot particle plasma lies the proposed epoch of cosmic inflation. Inflation is a period of accelerated expansion in the very early universe. In many models, the scale factor grows by an enormous amount while a field, or some equivalent form of energy, maintains nearly constant energy density. The expansion is sometimes described as faster than light. No object locally outruns a nearby light beam. Rather, the distance between widely separated comoving regions can increase at an effective rate greater than light speed because spacetime itself is evolving. Inflation was developed to address several puzzles. The first is the horizon problem. The microwave background has almost the same temperature and directions that, in a simple non-inflationary extrapolation, would not have had time to exchange signals before last scattering. Inflation proposes that these regions were once part of a much smaller causally connected domain. They could approach thermal uniformity before rapid expansion carried them far apart. The second is the flatness problem. In a universe governed by the usual equations, departures from the critical density tend to grow relative to the precisely balanced case. The observed geometry is very close to flat, which would require an extremely special early value without another mechanism. Inflation drives the observable region toward flatness, just as a small patch on a sufficiently large curved surface appears nearly flat. The third is the relic problem. Some high-energy theories predict heavy particles or defects, such as magnetic monopoles, that would be produced abundantly in early phase transitions. A long enough period of inflation would dilute pre-existing relics until almost none remained in the observable region. Inflation also offers a mechanism for primordial fluctuations. Quantum fields cannot be perfectly still. They fluctuate. During accelerated expansion, microscopic fluctuations can be stretched to scales much larger than the region over which local processes can smooth them. After inflation ends, these perturbations re-enter the horizon at later times and appear as small variations in density and curvature. The observed fluctuations have several properties expected in simple inflationary models. They are nearly scale invariant, mostly adiabatic, close to Gaussian, and coherent in phase in a way that produces the acoustic peak pattern. These are important successes. They are not a unique fingerprint proving one specific inflationary field. Many models can produce similar predictions. Alternative early universe scenarios attempt to generate the same initial conditions through bounces, contracting phases, or other mechanisms. Most face their own challenges, but the observational question remains open. One especially sought signal is a background of primordial gravitational waves. Inflationary tensor fluctuations could imprint a curling beam mode pattern in CMB polarization. Experiments have detected beam modes produced by gravitational lensing, but no primordial tensor signal has been confirmed. Current limits exclude some simple high-energy inflation models while leaving many others possible. The absence of primordial beam modes so far does not disprove inflation. Some models predict a signal far below present sensitivity. It does mean that the energy scale and mechanism remain uncertain. The duration of inflation is also expressed indirectly. Cosmologists often say it lasted at least around 50 to 60 e-folds for scales relevant to our observable universe, though the exact requirement depends on reheating and the model. An e-fold is a multiplication of the scale factor by the number e, repeated dozens of times. Even a microscopic region becomes enormously larger. What drove inflation is unknown. A hypothetical scalar degree of freedom is commonly called the inflaton, but this is a placeholder for a mechanism rather than a discovered particle. The Higgs field has inspired models, as have axion-like fields, modified gravity, and more complicated multi-field systems. None is established as the origin of inflation. Inflation must also end. In many models, the energy that sustained accelerated expansion is transferred into particles and radiation through a process called reheating. The name does not mean the universe was completely cold beforehand. It means the energy associated with the inflationary state is converted into a hot plasma, establishing the thermal conditions of the conventional hot Big Bang. The reheating temperature is unknown and can vary widely among models. It should be high enough for later processes, including nucleosynthesis, to proceed normally. It need not be close to any particular grand unification scale. The details influence how an observed wavelength maps back to the inflationary epoch. Inflation does not automatically answer why there is a universe, why the inflating state existed, or whether time had an earlier phase. Some versions lead to eternal inflation, in which inflation ends in local regions while continuing elsewhere. This can produce a vast ensemble of causally separated domains, sometimes called a multiverse. Other versions do not require the same global picture. Eternal inflation is a theoretical consequence of certain models, not an observed fact. Questions about probabilities and testability remain difficult. It should not be presented as a known extension of the Big Bang. There is also a subtle question about beginnings. Inflation can push the hot, dense phase farther from a classical singularity, but it does not by itself provide a complete past eternal history. Quantum cosmology, bouncing models, emergent universe proposals, and other ideas attempt to describe an earlier boundary. No consensus has emerged. The responsible picture is therefore neither dismissal nor certainty. Inflation is the leading framework for explaining the smoothness, flatness, and initial perturbations of the observable universe. Its broad predictions fit the data well. Its fundamental cause, precise dynamics, energy scale, and relation to any absolute beginning remain unknown. After any inflationary phase and reheating, the universe enters the portion of the story more directly connected to known particle physics. It is useful to imagine not a cloud of familiar objects, but a thermal population. Particles are continually created, destroyed, scattered, and transformed. At sufficiently high temperature, the energy of collisions exceeds the rest mass of many species. Matter and radiation exchange energy rapidly enough to approach equilibrium. The word particle can also be misleading here. Quantum fields are fundamental in the Standard Model. What we call particles are excitations of those fields. In the early universe, the relevant question is which excitations can exist abundantly at a given temperature and how quickly they interact compared with the expansion rate. At energies above the electroweak scale, the distinction between electromagnetic and weak interactions changes. The Higgs field is in a high-temperature state, and the particles that later acquire mass through interaction with it behave differently. As cooling proceeds, electroweak symmetry is broken. The Higgs boson discovered at CERN in 2012 confirmed the existence of the Higgs field and the central mechanism by which elementary particles acquire mass in the Standard Model. Accelerator experiments do not recreate the whole early universe, but they test the same local laws under high-energy conditions. The electroweak transition in the Standard Model is expected to be a smooth crossover rather than a violent first-order phase transition for the measured Higgs mass. This detail matters for baryogenesis. A strongly first-order transition could provide the non-equilibrium conditions needed by some mechanisms, but the minimal Standard Model does not appear sufficient. At still lower temperature, though still unimaginably hot, the strong interaction changes the form of matter. Today, quarks are confined inside hadrons such as protons and neutrons. Gluons carry the strong force between quarks. At temperatures of trillions of Kelvin, matter exists as a quark-gluon plasma, in which quarks and gluons are not confined into individual hadrons in the usual way. Heavy ion colliders can produce tiny droplets of this state for extremely brief times. The plasma behaves not like a thin ideal gas, but like an exceptionally low viscosity fluid. These experiments test quantum chromodynamics, the theory of the strong interaction, under conditions related to those of the universe a few microseconds after the hot beginning. As the cosmos cools through the QCD transition, quarks and gluons become bound into hadrons. For the matter content and conditions of the early universe, this is expected to be a crossover rather than a sharp first-order transition. Protons and neutrons emerge as stable members of a much larger temporary population that includes pions and many heavier hadrons. Most heavy species disappear as the temperature drops below the energy required to create them abundantly. They decay or annihilate. Their energy is transferred to lighter particles and radiation. This thermal sequence can sound like the universe is steadily assembling a set of permanent building blocks. In reality, creation and destruction continue in both directions while equilibrium holds. A species becomes a relic when interaction rates become too slow relative to expansion to maintain that equilibrium. This idea of freeze-out appears repeatedly. Neutrinos decouple. Neutron to proton conversion freezes. Nuclear reactions cease. A hypothetical dark matter particle might also freeze out with a surviving abundance. Each relic preserves information about the expansion rate and interactions at the moment it stopped following equilibrium. Dark matter must already influence the later universe, but its microscopic origin remains unknown. One possibility is a thermal relic. A new particle species may once have been abundant and in equilibrium. As the universe cooled, pair creation became difficult. Particles and antiparticles annihilated, but expansion eventually made encounters too rare for annihilation to continue efficiently. A residual population survived. This broad mechanism motivated weakly interacting massive particles, or WIMPs. Their predicted abundance can naturally fall near the observed dark matter density for interactions around the weak scale. Decades of sensitive searches have not produced a confirmed WIMP detection, so the allowed possibilities have narrowed. Dark matter may instead consist of axions or axion-like particles produced through non-thermal field dynamics. It could involve sterile neutrinos, hidden sector particles, primordial black holes in permitted mass ranges, or something outside current classifications. Cosmology measures how dark matter gravitates and clusters much more clearly than it reveals what dark matter is. The matter that is familiar to us presents a different mystery. At high temperature, particles and antiparticles should have been created in nearly equal numbers. When a particle meets its antiparticle, the pair can annihilate into radiation. If the early universe had contained exactly equal amounts of baryonic matter and antimatter and no process disturbed the balance, almost all protons and neutrons would have vanished. Instead, a small excess of matter survived. The imbalance is tiny when compared with the photon population. A rough way to express it is that after billions of matter-antimatter pairs annihilated, about one extra baryon remained for every billion or so background photons. That residual is the source of ordinary matter in stars, planets, air, oceans, and living cells. The process that generated the imbalance is called baryogenesis. Andrei Sakharov identified 3 broad requirements in 1967. Baryon number must not be perfectly conserved. The laws must distinguish matter from antimatter through violations of charge and charge parity symmetries. And the universe must pass through conditions away from thermal equilibrium, or an equivalent departure must occur, so reverse reactions do not simply erase the imbalance. The Standard Model contains some of these ingredients. Weak interactions violate charge conjugation and CP symmetry. Non-perturbative electroweak processes called sphalerons can change baryon and lepton number in the hot universe. But the known amount of CP violation and the character of the electroweak transition appear insufficient to generate the observed asymmetry in the simplest calculation. That points toward additional physics. Electroweak baryogenesis extends the particle content or Higgs sector to strengthen the phase transition and add CP violation. Leptogenesis proposes that heavy neutrino-like particles produced in asymmetry in leptons, part of which Sphaleron processes converted into a baryon asymmetry. Grand unified mechanisms allow very heavy particles to decay differently into matter and antimatter. These ideas connect cosmology to laboratory searches. Measurements of neutrino properties, electric dipole moments, rare decays, and new particles can restrict baryogenesis models. Yet no mechanism has been confirmed. The asymmetry is sometimes summarized as the question of why anything exists. That phrasing is emotionally powerful, but physically imprecise. Even in a matter-antimatter symmetric universe, radiation and perhaps other fields could remain. The specific mystery is why stable baryonic structures exist in the abundance observed. The answer was decided very early and expressed much later. A slight preference in microscopic reactions became galaxies full of stars. The visible complexity of the universe depends on an asymmetry too small to notice without precise counting. Antimatter has not disappeared from nature. It is produced in radioactive decays, cosmic ray collisions, particle accelerators, and energetic astrophysical environments. Positrons and antiprotons are routinely detected. What is absent is evidence for large regions made of antimatter arranged into anti-galaxies or anti-stars. Boundaries between large matter and antimatter domains would produce strong gamma-ray emission through annihilation. Searches have not found the expected signatures nearby. Observations therefore indicate that the accessible universe is overwhelmingly matter-dominated. The early thermal universe also contained neutrinos, photons, electrons, positrons, and other short-lived particles. As temperature fell below each mass threshold, the population changed. The energy and entropy of disappearing species were transferred to those still coupled. These transfers are why relic temperatures need not all be equal today. A species that decouples early misses later heating when other particles annihilate. Its temperature simply falls with expansion. Species still interacting share the released energy. This principle explains the expected temperature of the cosmic neutrino background and allows cosmology to count light particle species that existed when the universe was only seconds old. During the first seconds, leptons were central to the energy and reactions of the universe. Electrons and positrons were abundant. Neutrinos and antineutrinos of the three known flavors interacted with the plasma through the weak force. Photons continually created particle-antiparticle pairs when collisions carried enough energy, and those pairs annihilated back into radiation. Neutrinos are extraordinarily light and electrically neutral. They interact so weakly that trillions pass through a human body each second with almost no effect. In the early universe, density and temperature were high enough that even weak interactions occurred frequently. Expansion changed that balance. The reaction rate fell rapidly as temperature decreased, while the universe continued to grow. At an age of roughly 1 second and temperatures of order a few million electron volts, neutrinos began to decouple from the plasma. Decoupling was not a perfectly instantaneous switch. Different energies and interaction channels ceased maintaining equilibrium over a range of conditions. Detailed calculations include small distortions in the neutrino energy distributions and partial sharing of later heating. The simplified picture remains useful. After decoupling, most neutrinos traveled almost freely, their wavelengths stretching as the universe expanded. These relics should still surround us as the cosmic neutrino background. Its present temperature is predicted to be about 1.95 Kelvin, lower than the microwave background. The neutrinos are so low in energy that direct detection is extraordinarily difficult. Experiments have proposed using neutrino capture on radioactive nuclei. a reaction that would not require the incoming neutrino to exceed an ordinary detection threshold. No direct detection has yet been achieved. The neutrino background is nevertheless observed indirectly through its gravitational and thermal effects. During nucleosynthesis, the neutrino energy density influences the expansion rate. A faster expansion leaves less time for neutrons to convert or decay before nuclei form, changing the helium abundance. In the CMB, freely streaming neutrinos alter the acoustic oscillations and leave a subtle phase shift in the peaks. Large-scale structure is affected because massive neutrinos move rapidly and suppress clustering below certain scales. These effects are consistent with a background of roughly 3 active neutrino species. Cosmologists often express the result through an effective number called ineffective. It is not exactly 3 because neutrino decoupling is incomplete and quantum corrections matter. The standard prediction is slightly above 3. Measurements agreeing with that value provide a remarkable test. They indicate that the universe at an age of seconds contained the expected light particle content. Additional very light species, sometimes called dark radiation, would alter the value and are constrained by the combination of CMB and nucleosynthesis observations. Soon after neutrino decoupling, the temperature fell below the electron rest mass scale. High-energy photons could no longer replace electron-positron pairs as efficiently as the pairs annihilated. Most positrons disappeared with electrons, producing photons. A small excess of electrons remained because the surviving protons required negative charge to preserve overall electrical neutrality. The number of those electrons was tiny compared with the number of pairs that had existed earlier. Because photons were still coupled to the annihilating electrons and positrons, they received most of the released entropy. The neutrinos had largely decoupled and received less. This produced the persistent temperature difference between the photon and neutrino backgrounds. At this stage, the universe was seconds old. It contained an immense bath of photons, relic neutrinos, protons, neutrons, and the electrons needed to balance the proton charge. There were no stable atoms. Photons were still energetic enough to tear them apart immediately. The ratio of neutrons to protons was also changing. Weak reactions could convert neutrons into protons and protons into neutrons while equilibrium held. Because a neutron is slightly heavier, lower temperatures favored protons. As the weak reaction rates fell below expansion, the ratio froze at roughly 1 neutron for every 6 protons, then declined further as free neutrons decayed. This ratio became the clock that set the helium abundance. Almost every neutron that survived until nuclear reactions began would eventually enter helium-4. The delay before stable deuterium could form therefore mattered enormously. The universe was ready to build its first nuclei, but for a brief interval the radiation remained too destructive for the process to proceed. Big Bang nucleosynthesis began when the universe was only a few minutes old. The temperature had already fallen from billions of degrees, but that did not immediately allow complex nuclei to survive. The first step was the formation of deuterium, a nucleus containing 1 proton and 1 neutron. Deuterium is weakly bound compared with helium. A sufficiently energetic photon can break it apart. The early universe contained an enormous number of photons for every baryon. So even after the average photon energy dropped below the deuterium binding energy, the high-energy tail of the photon distribution continued to destroy newly formed deuterium. This delay is called the deuterium bottleneck. Expansion eventually cooled the radiation enough that deuterium survived faster than it was destroyed. Once that happened, nuclear reactions proceeded rapidly. Deuterium combined with protons or neutrons to form helium-3 and tritium. Further reactions built helium-4, whose tightly bound nucleus contains 2 protons and 2 neutrons. Helium-4 is exceptionally stable. Nearly all neutrons available at this time ended inside helium-4. The neutron-to-proton ratio therefore translates directly into a helium mass fraction near 25%. The remaining baryons were mostly protons, which later became hydrogen nuclei. Small amounts of deuterium and helium-3 survived. Reactions involving helium-3 and helium-4 also produced beryllium-7, which later decayed into lithium-7, along with a smaller direct contribution to lithium. The process ended quickly. After roughly 20 minutes, expansion had reduced density and temperature enough that nuclear collisions became too infrequent for substantial further fusion. Why did the Big Bang not build carbon, oxygen, and heavier elements as stars later would? Time and density were part of the answer. The nuclear burning interval was brief. There were also no stable nuclei with mass numbers 5 or 8, creating gaps in the reaction network. Stars overcome the mass 8 gap through the triple alpha process, in which 3 helium nuclei combine through a short-lived beryllium-8 state. That requires sustained high density and temperature. The expanding early universe cooled too quickly. Big Bang nucleosynthesis therefore left a chemically simple cosmos: hydrogen, helium, and traces of a few light isotopes. Carbon and oxygen would wait for stars. The calculation is one of the cleanest bridges between particle physics and astronomy. Nuclear reaction rates can be measured in laboratories, though some require careful extrapolation to the relevant energies. The neutron lifetime is measured experimentally. The expansion rate follows from the energy density and general relativity. The baryon density is constrained independently by the microwave background. From these inputs, a reaction network predicts the abundances. Deuterium is especially valuable. Stars generally destroy it when material is cycled through hot interiors. Significant ordinary astrophysical processes do not replenish it in a way that would mimic a primordial abundance across pristine gas. The highest deuterium fractions are therefore sought in low metallicity clouds that have experienced little stellar processing. These clouds can be detected when they absorb light from a more distant quasar. Hydrogen and deuterium produce slightly shifted absorption lines because their nuclear masses differ. The measurement is difficult, but the best systems provide a precise primordial deuterium estimate. Helium-4 is measured mainly in low metallicity ionist regions. Stars have produced additional helium, so astronomers examine environments with very little oxygen and other heavy elements, then extrapolate towards zero metallicity. Temperature structure, atomic emission physics, and stellar absorption introduce systematic uncertainty. The inferred deuterium and helium abundances agree with the standard calculation and with the baryon density from the CMB. This agreement also tests the expansion rate during the first minutes. Additional light particles would increase the radiation density, accelerate expansion, and alter the neutron fraction and helium yield. A changing gravitational strength or decaying exotic particle could also disturb the abundances. The observed pattern leaves limited room for such changes. Helium-3 is harder to use because stars can both create and destroy it, and galactic chemical evolution complicates the connection to the primordial value. Lithium-7 presents the famous exception. The standard calculation, using the baryon density measured from the CMB, predicts roughly 3 times more lithium-7 than appears in the atmospheres of many old, metal-poor halo stars. Those stars display a nearly constant lithium abundance, known as the Spite Plateau. The discrepancy may be astrophysical. Lithium is fragile and can be destroyed at temperatures reached below a stellar surface. Diffusion, turbulent mixing, rotation, and early stellar evolution may reduce the visible abundance while leaving other elements less affected. Reconstructing the original lithium content of an ancient atmosphere is not simple. The discrepancy may involve nuclear inputs, though extensive work has not found an ordinary reaction rate change large enough to solve it cleanly. It may involve new particles or altered early universe conditions, but such proposals must preserve the successful deuterium and helium predictions. The lithium problem remains real. It is a reminder that a model's success is not the same as perfection. Still, the broad nucleosynthesis result is extraordinary. A calculation of nuclear reactions during a few minutes of cosmic time predicts the dominant chemical composition of pristine matter billions of years later. Most of the helium in the universe did not originate in stars. Stars create helium, but the near-universal baseline was already present before the first star existed. The first nuclei formed in minutes. Neutral atoms would require hundreds of thousands of years. Between those events, the universe remained a luminous plasma, opaque in every direction. After nucleosynthesis, the universe entered a long interval of cooling without the formation of new stable elements. The ingredients were simple: hydrogen nuclei, helium nuclei, electrons, photons, neutrinos, dark matter, and perhaps other relics. Yet their collective behavior was rich. Photons scattered constantly from free electrons. The mean distance a photon could travel before another scattering was very short compared with cosmic scales. Light did not cross the universe in straight lines. It diffused through an opaque plasma. Opaque does not mean dark. The plasma was filled with thermal radiation. If an observer could somehow exist within it, there would be no clear view in any direction. Only a nearly uniform brilliance surrounding every point. Radiation initially contributed more to the total energy density than matter. Expansion changes the two components differently. Matter density falls with the volume, proportional to the inverse cube of the scale factor. Radiation is diluted by volume as well, but each photon's wavelength is also stretched and its energy reduced. Radiation density therefore falls with the inverse fourth power. Eventually, matter overtook radiation. This matter-radiation equality occurred tens of thousands of years after the hot beginning, before recombination. The transition altered the growth of perturbations and left signatures in the CMB and matter power spectrum. Dark matter had already begun to collect gravitationally. Ordinary baryons could not collapse freely because their electrons remained coupled to radiation. Photon pressure resisted compression. Dark matter, assuming it was cold and weakly interacting, did not feel that pressure and formed growing potential wells. The photon baryon plasma oscillated within those wells. Gravity pulled material into an overdense region. Compression heated the radiation and increased pressure. Pressure pushed outward. The region expanded and cooled, after which gravity began another compression. These were sound waves, although the medium and speed were unlike sound in air. The waves did not begin at one center. Primordial fluctuations existed across a range of scales. Each mode entered causal contact at a different time and began its own oscillation. By the time photons decoupled, different modes had reached different phases. The acoustic peaks in the microwave background are a frozen record of those phases. The plasma also carried bulk velocities. Scattering from moving electrons shifted the radiation. Gravitational potentials changed photon energies as light climbed out. On the largest scales, the combination of intrinsic temperature and gravitational redshift produces the Sachs-Wolf effect. Along the later journey, evolving gravitational potentials add an integrated contribution. Meanwhile, photons diffused from hotter regions into cooler ones. On small scales, this diffusion erased fluctuations, an effect called silk damping. The damping tail of the CMB power spectrum records the thickness and transport properties of the plasma near last scattering. At an age of about 380,000 years, the average temperature had fallen to roughly 3,000 Kelvin. Electrons could remain bound to protons long enough for neutral hydrogen to accumulate. The process is called recombination for historical reasons inherited from atomic and plasma physics, even though it was the first cosmic formation of neutral hydrogen. It does not imply that atoms had existed before inflation and were being assembled again. Helium recombined somewhat earlier through several stages. Hydrogen recombination dominated the later change in opacity. Even at 3000 Kelvin, the average photon energy was not the only consideration. As with deuterium, the large photon-to-baryon ratio meant that the high-energy tail could ionize atoms. Direct capture into the ground state often produced a photon capable of ionizing another atom. The detailed path, therefore, involved excited states, two-photon decay from metastable hydrogen, and the gradual escape of resonance photons as expansion redshifted them. Recombination was not instantaneous. The fraction of free electrons declined across a finite range of redshift. As scattering became less frequent, photons decoupled and began traveling mostly freely. The surface of last scattering is therefore not an infinitely thin wall. It has a thickness in time and distance described by a visibility function, the probability that a photon lasts scattered at each epoch. The photons released then are the CMB we receive now. Their wavelengths have expanded by a factor of roughly 1100. Radiation that had a thermal temperature near 3000 Kelvin now appears at about 2.7 Kelvin in the microwave range. The universe became transparent to this radiation, but not perfectly transparent at every wavelength. Neutral hydrogen absorbs photons energetic enough to ionize it and interacts strongly at specific spectral lines. Dust did not yet exist because stars had not produced heavy elements. The phrase transparent means that most CMB photons could finally propagate across cosmological distances without repeated scattering. This event separated matter from radiation dynamically. Photon pressure no longer held ordinary matter in the same acoustic fluid. Baryons began falling more effectively into the dark matter potential wells. Their earlier oscillations did not vanish entirely. They left a preferred comoving separation in the distribution of matter. That relic is the baryon acoustic oscillation scale. Imagine an initial overdensity containing dark matter, baryons, and photons. Dark matter remains near the original center, while a spherical sound wave of baryons and photons travels outward. At decoupling, the photons stream away. The baryonic shell stalls at a characteristic distance, while gravity later draws matter both toward the center and toward the shell. Billions of years of nonlinear evolution blur the pattern, but a slight excess probability remains for finding pairs of galaxies separated by that characteristic comoving scale. Astronomers measure the feature statistically across millions of galaxies and quasars. Because the physical scale can be calibrated from early universe physics, it acts as a standard ruler. Its apparent size across the sky and along the line of sight reveals distances and the expansion rate at different redshifts. The same physics is therefore visible twice. As acoustic peaks in the CMB at 380,000 years and as a preferred clustering scale in galaxies billions of years later. This connection is one of the most elegant consistency checks in cosmology. Recombination also created a neutral universe ready for chemistry, but the chemistry was extremely limited. Hydrogen atoms could form molecular hydrogen through slow gas phase reactions. Tiny amounts of molecules such as hydrogen deuteride and helium hydride ions existed. Without dust grains and heavy elements, cooling pathways were sparse. Gravity now had time to work in darkness. The small fluctuations preserved in the CMB were about to become the first dense clouds, the first stars, and the first sources of new light. After recombination, the universe entered the Dark Ages. The name does not mean that nothing happened. gravity continued to deepen the small density variations. Gas flowed into dark matter halos. Molecules formed in trace amounts. The microwave background cooled from visible and infrared wavelengths into the microwave band. It was dark because there were not yet stars. Neutral hydrogen filled most of intergalactic space. The gas was initially warmer than it would have been from expansion alone because residual electrons continued exchanging energy with CMB photons. Later, matter cooled more rapidly than the radiation. This temperature difference would become important for the 21 centimeter signal of neutral hydrogen. The 21 centimeter line arises from a subtle transition in the hydrogen atom. The electron and proton can have their spins aligned or opposed. A transition between these states emits or absorbs a radio photon with a wavelength of about 21 centimeters in the atom's rest frame. Cosmic expansion stretches the wavelength, so observations at different radio frequencies correspond to different eras. In principle, neutral hydrogen can provide a three-dimensional map of the dark ages and cosmic dawn across a range of times that no ordinary galaxy survey can reach. The signal is faint and hidden beneath foreground radio emission from the Milky Way and human technology that can be thousands of times brighter. Experiments such as HERA seek a statistical detection of fluctuations from cosmic dawn and reionization. As of the mid-2020s, increasingly strong upper limits have been measured, but a definitive tomographic detection remains a major goal. The first stars formed inside small dark matter halos where gas became dense enough to cool and collapse. Without carbon, oxygen, or dust, the gas relied mainly on molecular hydrogen for cooling. That process was less efficient than cooling in later enriched clouds, so the characteristic fragments may have been relatively massive. These first stars are commonly called population 3, a historical name meaning a population with essentially no elements heavier than helium. No individual population 3 star has yet been observed directly. Simulations suggest that the population may have included many massive stars, but probably not one single universal mass. Some may have lived only a few million years before exploding as supernovae or collapsing into black holes. Others in lower mass ranges, if any formed and survived, could still exist, but searches have not found a truly metal-free star. The first supernovae changed the chemistry of the universe. They dispersed carbon, oxygen, silicon, iron, and other elements into surrounding gas. Later stars formed from material carrying the fingerprints of those explosions. Astronomers search for those fingerprints in extremely metal-poor stars in the Milky Way and nearby dwarf galaxies. The abundance pattern in one old star can reveal whether its birth cloud was enriched by a faint supernova, a very massive explosion, or several earlier sources. The first stars also began altering the intergalactic medium with radiation. Ultraviolet photons ionized hydrogen around each source, creating expanding bubbles of ionized gas. Early galaxies contained groups of stars and perhaps accreting black holes, producing more radiation. Over hundreds of millions of years, the bubbles grew and overlapped. This process is called cosmic reionization. The word sounds like a return because hydrogen had been ionized before recombination. The early plasma became neutral, then the first luminous sources ionized much of the intergalactic hydrogen again. Reionization was patchy rather than simultaneous. Dense regions formed galaxies first and generated large bubbles. Neutral islands survived elsewhere. The progress depended on the number of faint galaxies, the production of ultraviolet photons, and the fraction of those photons that escaped from galaxies into intergalactic space. By a redshift near 6, when the universe was approaching 1 billion years old, most intergalactic hydrogen was ionized, although neutral pockets and the exact end of the process remain subjects of measurement. Quasar spectra provide one probe. Neutral hydrogen absorbs light blueward of the Lyman alpha transition. At sufficiently high redshift, strong absorption creates a Gunn-Peterson trough. The changing absorption toward distant quasars traces the rising neutral fraction. The CMB provides another probe. Free electrons produced by reionization scattered a small fraction of the microwave photons, generating large-scale polarization and slightly suppressing small-scale anisotropies. The optical depth inferred from this effect constrains the integrated history of reionization. Galaxies themselves supply the sources. Their ultraviolet luminosity functions estimate how much ionizing radiation was available, including contributions from galaxies too faint to detect individually. Emission lines and spectral breaks reveal the conditions of their gas and the surrounding intergalactic medium. The James Webb Space Telescope transformed this field by combining deep infrared imaging with spectroscopy. It has confirmed luminous galaxies at redshifts above 14, corresponding to less than 300 million years after the hot beginning in the Standard Model. One such system, MOMZ14, has a spectroscopic redshift around 14.4 and is seen when the universe was about 280 million years old. The existence of bright systems so early was surprising. Some initial photometric candidates turned out to lie at lower redshift or to have properties distorted by strong emission lines. But spectroscopy has confirmed that substantial star formation was already occurring during the first few hundred million years. This does not overturn the Big Bang or the basic cold dark matter framework. It does force models of early star formation, feedback, dust, and galaxy growth to work efficiently. The earliest observed galaxies may occupy rare, rapidly developing halos rather than representing the average region. Their brightness also creates a selection effect. Webb first finds objects capable of being seen. Fainter and perhaps more typical galaxies remain below current limits. Gravitational lensing by foreground clusters can magnify some of them, at the cost of uncertainty in the magnification. Early galaxies were not miniature versions of the modern Milky Way. Many were compact, irregular, and rapidly changing. Gas flowed inward. Massive stars produced intense ultraviolet radiation. Supernovae drove material outward. Black holes may have grown unexpectedly early in some systems. The origin of the first black hole seeds is another open question. They may have been remnants of massive population 3 stars. Dense star clusters may have produced larger seeds through runaway collisions. In special halos, gas might have collapsed directly into black holes without first forming ordinary stars. Different channels may all have contributed. Small seeds must accrete near their physical limits for long periods to become the billion solar mass quasars observed within the first billion years. Finding active black holes at progressively earlier times tests how that growth occurred. The Dark Ages therefore ended gradually. One region could contain a shining galaxy, while another remained neutral and unilluminated. There was no universal morning in which the entire cosmos brightened at once. The first light changed more than visibility. Radiation heated intergalactic gas and made it harder for the smallest halos to collect material. Supernovae enriched the medium and altered cooling. New elements enabled smaller clouds and lower mass stars. The deaths of the first stars prepared the conditions for more varied generations. This feedback transformed a chemically simple universe into an ecosystem of galaxies. The 21-centimeter signal may eventually show the transformation as a moving landscape. Cold neutral gas absorbing against the CMB, X-ray sources heating the medium, ionist bubbles appearing around galaxies, and the final neutral islands disappearing. Such a map would fill the longest observational gap in cosmic history. The CMB gives a precise image at 380,000 years. Webb and other telescopes reveal galaxies a few 100 million years later. Between them lies a largely unseen interval during which ordinary matter crossed from smooth gas to the first luminous structures. The beginning of everything familiar was not one event. It was a sequence of thresholds. First nuclei, then atoms, then molecules, then stars, then heavy elements, then galaxies capable of preserving long histories. The Big Bang leaves open questions deeper than the timeline it explains. The most common is simple to ask: what caused it? The difficulty begins with the word "it." The hot Big Bang is a well-tested early phase, not necessarily a single event with a known boundary. Inflation, if it occurred, would precede the thermal plasma. A quantum gravity phase might precede inflation. An earlier contracting universe or another form of space-time might lie beyond that. Or ordinary temporal language may fail near the boundary. A cause normally occurs earlier than its effect. If time itself has a finite beginning in the relevant theory, asking for an earlier cause may import a relationship that cannot exist. If time extends through an earlier phase, then the question becomes meaningful again. Current observations do not decide between these possibilities. General relativity provides an important but incomplete clue. When the large-scale expansion is extrapolated backward under broad assumptions, geodesics cannot be extended indefinitely. Density and curvature grow, and the classical description becomes incomplete. The singularity theorems associated with Roger Penrose, Stephen Hawking, and others showed that this incompleteness is not merely an artifact of perfect spherical symmetry. Yet a singularity in a classical equation is not a photograph of a physical object. It marks the edge of the theory's domain. The center of a classical black hole solution contains a similar breakdown. Physicists do not assume that infinity is a substance hidden there. They infer that quantum gravity must modify the description before the classical divergence is reached. Several research programs attempt to provide that modification. The Hartle-Hawking no-boundary proposal applies a quantum description to the universe as a whole. Near the earliest regime, the mathematical distinction between time and a spatial direction changes. The geometry can close smoothly rather than ending at a sharp edge. The familiar analogy is Earth's surface at the South Pole. The surface has a southernmost point, but no boundary beyond which one can continue farther south. The analogy is limited. The proposal is mathematical, depends on how a path integral over geometries is defined, and does not produce one universally accepted prediction. Its importance lies in showing that a finite past need not resemble an ordinary first moment preceded by nothing. The tumbling proposal associated with Alexander Vilenkin offers a different quantum cosmological boundary condition. Popular descriptions sometimes call it creation from nothing, but nothing in this setting is not ordinary empty space. It is the absence of a classical spacetime described within a particular quantum framework. The language should not be confused with a demonstrated physical event. Loop quantum cosmology, inspired by loop quantum gravity, replaces the classical singularity in some simplified models with a quantum bounce. A contracting phase reaches a maximum density and transitions into expansion. Whether the result survives in a complete theory with realistic fields and inhomogeneities is under study. Ekpyrotic and cyclic scenarios use a slow contracting phase to smooth and flatten the universe before a bounce. Some versions arose from higher dimensional brane ideas. They can produce nearly scale invariant perturbations under suitable conditions, but constructing a stable, non-singular transition and matching all observations is difficult. Conformal cyclic cosmology, proposed by Roger Penrose, imagines that the remote future of one cosmic aeon can be mathematically connected to the Big Bang of the next after scale loses physical meaning. Proposed observational signatures remain controversial and have not gained broad confirmation. Emergent universe models attempt to begin from a long-lived state that later enters expansion. Other approaches describe space-time and gravity as phenomena emerging from more fundamental quantum information or interactions. These ideas are not interchangeable. They use different mathematics, make different assumptions, and face different problems. Listing them does not mean science has several equally confirmed answers. It means the missing theory permits a landscape of serious possibilities. Observation may still distinguish some of them. A pre-inflationary phase could leave features in the largest scale, see MB fluctuations. A bounce might alter the primordial power spectrum or non-Gaussianity. Cosmic strings or other relics could survive. Primordial gravitational waves might carry a characteristic spectrum. Spectral distortions of the CMB could reveal energy release at epochs inaccessible to ordinary images. The challenge is that inflation or other rapid expansion can erase earlier information. Cosmic variance also limits how well we can measure the largest observable modes because the universe provides only one sky and a finite number of independent regions. The word before may therefore be both physically meaningful and observationally hidden. Eternal inflation introduces another possibility. Quantum fluctuations can cause inflation to end in some regions while continuing in others. Local reheating regions become pocket universes, potentially with different low-energy conditions. Our hot Big Bang would then be a local beginning inside a much larger inflating structure. This multiverse picture follows from some models, but not all. It raises difficult questions about defining probabilities in an infinite ensemble and about whether other domains can leave observable traces. No confirmed observation requires a multiverse. The anthropic principle is sometimes invoked within such frameworks. If physical conditions vary across domains, observers can arise only where the conditions permit complex structures. This may help interpret apparent fine-tuning, but it does not replace the task of calculating what varies, how often, and under what measure. The Big Bang also leaves open why the laws and constants take their observed forms. Cosmology can infer the baryon density, dark matter abundance, fluctuation amplitude, and expansion parameters. It does not yet explain why those values emerged. Some may follow from deeper dynamics. Some may be environmental. Some may be initial conditions. The distinction is unknown. There is a temptation to fill this boundary with confident language from either direction. One can claim that science has proven an absolute beginning, or one can claim that any beginning has been ruled out by a preferred speculative model. Neither statement is justified. The careful conclusion is narrower and stronger. The observable universe evolved from a hot, dense, expanding state. The standard model describes that evolution with exceptional success from the first minutes onward and with increasing theoretical uncertainty at earlier times. Classical general relativity becomes incomplete when extrapolated far enough back. A tested quantum description of that boundary does not yet exist. This is not an empty admission. It defines one of the clearest frontiers in physics. The missing answer links quantum theory, gravity, thermodynamics, particle physics, and the meaning of time. Any successful theory must reproduce the ordinary universe at later times, explain or accommodate inflation like initial conditions, remain mathematically consistent, and produce predictions that observations can test. The question of origin is therefore not outside science merely because it is difficult. Parts of it may become scientific as theories sharpen and measurements improve. Other parts may remain underdetermined by anything observable from our cosmic horizon. For now, the Big Bang is best understood not as an explanation of why there is something rather than nothing, but as the earliest well-supported chapter in the history of the something we can observe. There is a specific part of the Big Bang picture that creates many misunderstandings: the singularity. In a simple classical model, The scale factor approaches zero when the equations are run backward. Density, temperature, and curvature grow without bound. This mathematical limit is often drawn as the first point on a timeline and described as an object of infinite density. The drawing is not the physics. General relativity has been tested with extraordinary success, from clocks on Earth to black holes and gravitational waves. But it does not include the quantum nature of matter and space-time at the Planck scale. Applying the classical equations beyond that scale is like applying the equations of fluid flow to a single molecule. The theory is being asked to describe a regime outside the structure for which it was built. The singularity therefore indicates geodesic incompleteness. The classical spacetime cannot be extended farther along certain paths. It does not tell us what a complete theory would place there. This is why cosmologists can accept the hot Big Bang while remaining agnostic about a literal initial singularity. The successful predictions arise at later, finite temperatures and densities. Nucleosynthesis does not require an actual infinity. The CMB does not show the singularity. Galaxy expansion does not depend on knowing the final quantum boundary. The situation resembles reconstructing the history of a river. Measurements downstream can establish that the water came through a narrow mountain valley even if fog hides the spring. The uncertainty at the source does not erase what can be learned from the flow. The Big Bang is also frequently described as the universe expanding from a point. That sentence can be useful only if point refers to the vanishing separation of locations in an idealized finite comoving region. It becomes wrong when imagined as a tiny ball sitting inside empty space. The entire observable region was once much smaller in physical scale, but the total universe may extend beyond that region, perhaps infinitely. An infinite space does not become finite merely because the scale factor shrinks. Consider an infinite number line whose distance unit is reduced. Every pair of marked neighboring points can become arbitrarily close while the line remains infinite. The density can diverge everywhere without all of space occupying one location in a larger container. If space is finite, it need not have an edge. A two-dimensional analogy is the surface of a sphere. It has finite area but no boundary line. A three-dimensional space can possess an analogous global topology, though it cannot be visualized from outside in the same way. Current measurements show that the observable universe is close to spatially flat. Flatness does not prove infinity. A finite space can have flat geometry if it wraps through a topology like a three-dimensional torus. Searches for repeated patterns in the CMB constrain some compact topologies, but the global form remains unknown. There is no observed center of cosmic expansion. Every observer participates in the same large-scale flow. A galaxy 1 billion light-years away is not moving away because we occupy the explosion site. From that galaxy, the Milky Way would also be receding, and more distant systems would recede more rapidly on average. There is also no known outer edge toward which galaxies travel. The observable universe has a horizon, but a horizon is not a wall. It is a limit on communication. We see only regions whose light has had time to reach us through an evolving space-time. Because the universe has expanded while light traveled, the present distance to the matter that emitted the oldest observable light is much greater than 13.8 billion light-years. The radius of the observable universe in present comoving distance is about 46 billion light-years, making its present diameter roughly 93 billion light-years. This does not mean light traveled faster than light. A CMB photon covered a changing distance while space between comoving locations expanded. The source region is now much farther away than the light travel time multiplied by a fixed distance scale would suggest. The distinction among distances matters in cosmology. Look-back time tells how long the photon traveled. proper distance refers to separation at a chosen cosmic time. Moving distance factors out the expansion and labels locations in a coordinate grid that grows with the universe. Luminosity distance and angular diameter distance connect observations to brightness and apparent size. These distances agree nearby and diverge at large redshift. Many apparent paradoxes arise from mixing them. Some galaxies currently recede from us faster than light in the sense that their proper distance increases by more than 1 light-year per year. This does not violate special relativity. Special relativity forbids an object from passing a nearby observer through local space faster than light. General relativity permits the distance between sufficiently remote moving objects to grow at an arbitrarily large rate. We can even observe light from regions whose present recession rate exceeds light speed. The photon may initially have been carried away from us by expansion, then later entered a period when the changing Hubble radius allowed it to make net progress toward us. The cosmic event horizon is different from the particle horizon. The particle horizon marks the farthest region that could have influenced us since the early universe. The event horizon marks a limit beyond which events occurring now will never send signals that reach us, assuming accelerated expansion continues. If dark energy remains close to a cosmological constant and accelerated expansion continues, some currently visible galaxies will eventually become causally unreachable and fade from view. Their older light will continue to arrive for a time, increasingly redshifted. Future observers in the distant Milky Way Andromeda remnant may then see a much emptier sky and have less direct evidence for cosmic expansion. The Big Bang itself is not a visible surface behind the CMB. Earlier photons were repeatedly scattered, so electromagnetic vision ends at last scattering. Neutrinos could carry information from the first seconds, and gravitational waves could in principle carry information from far earlier, but those backgrounds remain difficult to detect. When astronomers say that looking far away is looking back in time, they mean that light has a finite travel speed. A galaxy seen at high redshift is observed as it was, not as it is now. There is no universal telescope view of the present across the whole cosmos. This also means the CMB sphere is centered on every observer. An observer in another galaxy would see their own last scattering sphere, overlapping ours, but not identical. The observed microwave sky is not a shell with Earth at a physical center. It is the intersection of our past light cone with the era when photons decoupled. The past light cone is a useful way to picture observation. Every signal reaching us now lies on a path through space-time ending at the present observer. More distant signals left earlier. At the CMB, the cone intersects an opaque era. Before that boundary, information must come through messengers other than freely traveling light or through imprints carried forward into the CMB. The question of what the universe expands into can now be answered more carefully. Expansion is a change in the metric, the rule that assigns distances between comoving locations. It does not require an external volume. General relativity describes the geometry intrinsically. Asking what lies outside all space may be like asking for a point north of the North Pole, but only if the universe is complete without a boundary in the relevant model. Some speculative higher dimensional theories embed our observable dimensions in a larger structure. In those models, an external geometry can have physical meaning. Observation has not established that such an embedding exists. Likewise, the statement that time began at the Big Bang is model-dependent. Classical expanding solutions are incomplete in the past. Some quantum proposals have no earlier time. Others include a prior phase. Science has not selected one. What can be stated without ambiguity is that the ordinary cosmic time used to describe galaxies, atoms, and radiation cannot be extrapolated through the classical singularity using known equations. The boundary between knowledge and imagery matters because the wrong picture creates unnecessary puzzles. A tiny bomb requires surrounding space. An explosion has a center. Flying debris moves through a static background. The Big Bang requires none of these. It is a history of changing scale, temperature, density, composition, and structure throughout the region we observe. The earliest universe was not far away in one direction. It is far away in time in every direction. Every line of sight, traced deeply enough, approaches the same hot cosmic past. One of the most striking features of the Big Bang framework is the connection between the very small and the very large. A quantum field fluctuating at an early epoch may become a density pattern extending across millions of light years. The lifetime of a neutron helps determine the helium content of galaxies. The mass of a neutrino influences the growth of the cosmic web. Atomic energy levels determine the moment when the universe becomes transparent. Cosmology is therefore not only astronomy conducted at great distance. It is particle physics, nuclear physics, atomic physics, thermodynamics, and general relativity applied to the same evolving system. The initial fluctuation spectrum provides the clearest example. If inflation generated the perturbations, quantum fluctuations in one or more fields were stretched to macroscopic scales. After inflation, these fluctuations became curvature perturbations. Later, they entered causal contact, drove acoustic waves, formed dark matter halos, and eventually influenced where galaxies appeared. An individual galaxy cannot be traced to one identified quantum event. The connection is statistical. The early theory predicts the distribution of amplitudes and correlations. Surveys measure the later distribution of matter. The agreement across an immense range of scale is the remarkable part. Nucleosynthesis provides another connection. The helium fraction depends on the competition between weak reactions and expansion around the first second, the neutron lifetime, the deuterium binding energy, and the baryon to photon ratio. A measurement in a distant low metallicity gas cloud tests all of them together. Recombination connects atomic transitions to cosmic geometry. The two-photon decay rate of excited hydrogen affects the electron fraction. That electron fraction changes the thickness of last scattering. The thickness alters CMB anisotropies. Those anisotropies help determine the age and composition of the entire observable universe. Neutrinos connect laboratory oscillation experiments with structure across galaxies. Experiments show that neutrinos have mass because they change flavor during travel. Cosmology constrains the sum of their masses because fast-moving neutrinos resist clustering on small scales and modify the CMB and matter distribution. The identity of dark matter would create an even larger bridge. A particle detected in an underground experiment or accelerator could explain the invisible gravitational framework of galaxies. An axion detected through a weak electromagnetic conversion could connect a solution to a symmetry problem in the strong interaction with the formation of cosmic structure. The expansion history makes another bridge between local clocks and the universe as a whole. The age of the universe is calculated by integrating the inverse expansion rate over cosmic history. Matter slows expansion through gravity. Radiation dominates at the earliest times and changes the relation. Dark energy causes late acceleration. The present Hubble constant alone is not enough. The composition and evolution are required. Within lambda CDM, CMB measurements produce an age close to 13.8 billion years with very small formal uncertainty. That precision is conditional on the model. Allow additional curvature, changing dark energy, or new early components, and the uncertainty broadens. Independent age estimates provide a check. The oldest globular clusters and individual ancient stars must be younger than the universe. White dwarf cooling, stellar evolution, and radioactive dating all placed the oldest populations near, but below, the cosmological age within their uncertainties. The agreement was not always so comfortable. Earlier measurements sometimes implied a universe younger than its oldest stars. Improved stellar models, distance calibration, and the discovery of accelerated expansion resolved much of that historical age problem. Modern tensions are subtler. The Hubble tension compares early universe inference with late universe measurement. The S8 tension concerns the amplitude of matter clustering inferred from the CMB and some weak lensing surveys. Recent baryon acoustic oscillation results from DESI, combined with different supernova samples and the CMB, have produced hints that dark energy may evolve rather than remain a strict cosmological constant. The strength and interpretation of those hints depend on the datasets and parameterization. They do not yet establish a replacement for lambda CDM. They show that precision cosmology has entered a stage where small disagreements can point to calibration, astrophysical complexity, statistical fluctuation, or new physics. This is a very different situation from the early debate between steady state and a hot beginning. The broad thermal history is secure. The questions now concern refinements within and around the successful framework. How exactly did inflation work? What is dark matter? Is dark energy constant? What generated the baryon asymmetry? What is the neutrino mass ordering and total mass? Did the earliest universe contain additional light species? Did a phase transition leave a gravitational wave background? Each question can leave signals at multiple scales. A new particle changes reaction rates. Reaction rates change relic abundances. Relic abundances change expansion. Expansion changes the CMB and galaxy distribution. The universe functions as a laboratory that ran experiments at energies no human machine can reach. It did not label the apparatus or repeat the run for us. Cosmologists infer the setup from surviving traces. The traces overlap. A proposed solution to the Hubble tension must preserve nucleosynthesis, the CMB peaks, galaxy clustering, supernova distances, and stellar ages. A dark matter model must form halos while satisfying lensing, galaxy dynamics, the CMB, and laboratory limits. An inflation model must produce the observed perturbations without creating excluded non-Gaussianity or gravitational waves. This web of constraints is why the standard history is difficult to replace casually. Changing one early ingredient affects many later observations. The cosmos is large enough to contain billions of galaxies, yet its broad history can be constrained by a small set of physical laws. That simplicity should not be confused with inevitability. The laws, constants, and initial conditions could conceivably have been different. Why they take these forms remains unanswered. But once they are specified, the sequence becomes intelligible. Expansion cools the plasma. Cooling selects which particles survive. Reactions build nuclei. Atoms release radiation. Gravity amplifies fluctuations. Stars create new elements. Galaxies organize those stars across time. The small and the large are not separate stories. They are the same story viewed at different scales. The Big Bang was, from another perspective, extraordinarily quiet. Not quiet in energy. The early radiation field was intense, the temperature enormous, and particles collided continually. It was quiet in structure. Across large scales, matter and radiation were almost uniform. The density differences that later became galaxies were only tiny variations. There were no stars exploding, no black holes merging, no planets colliding, and no complicated chemical systems. The early observable universe was close to the smoothest state nature permits. This smoothness is connected to one of the deepest puzzles, the low entropy of the beginning. Entropy is often described as disorder, but that shorthand can mislead. More precisely, Entropy measures how many microscopic configurations correspond to the macroscopic state and how energy is distributed among available possibilities. A gas spreading through a room moves toward equilibrium because vastly more microscopic arrangements place molecules throughout the room than inside one corner. Heat flows from hot to cold because the combined equilibrium state is overwhelmingly more probable. The early universe was hot and close to thermal equilibrium in its matter and radiation. That sounds like high entropy. In those components, it was. Yet gravity changes the accounting. For a self-gravitating system, uniformity is not the maximum entropy state. Gravity causes matter to clump. Clumps can form stars, galaxies, and ultimately black holes. A black hole carries an enormous entropy proportional to the area of its event horizon. A universe filled with black holes would possess far greater gravitational entropy than the smooth early universe. The absence of strong gravitational clumping therefore represents an extremely special low entropy condition. This low initial gravitational entropy gives the arrow of time its cosmic foundation. On ordinary scales, we remember the past and not the future. Eggs break and do not spontaneously reassemble. Heat spreads. Stars consume concentrated nuclear fuel. Living systems maintain local order by releasing greater entropy into their surroundings. All these arrows align with the direction in which cosmic entropy increases from the special early state. The dynamical laws at microscopic scales are often nearly time reversal symmetric. If a film of a few particles colliding were played backward, the motion might still obey the equations. The difference between past and future enters through boundary conditions. The universe began in a state from which overwhelmingly many evolutions lead toward higher entropy. Why that state existed is not explained by saying entropy increases. The second law describes the evolution given a low entropy past. It does not provide the past condition. Inflation can smooth a region and dilute curvature and unwanted relics. It may help produce the observed homogeneity. But the inflationary state itself must possess suitable conditions, and debates continue over whether inflation fully explains or merely relocates the entropy problem. Roger Penrose emphasized this issue and proposed that the Weyl curvature associated with free gravitational degrees of freedom was constrained near the beginning. In a smooth expanding universe, Weyl curvature is small compared with the wildly irregular geometry associated with black holes. His Weyl curvature hypothesis is a proposed principle rather than an established law, but it focuses attention on the special gravitational character of the initial state. Other researchers approach the problem through quantum cosmology, statistical selection, inflationary attractors, or multiverse reasoning. None has produced a universally accepted explanation. The entropy puzzle is closely related to the title of this story. The beginning was quiet because gravity had almost no large structures to describe. The universe was not born with galaxies already arranged or black holes occupying every possible region. It began smooth enough for complexity to develop gradually. A perfectly uniform universe would remain uniform. No stars would form because no location would be denser than another. The early state was therefore balanced between two extremes. It was smooth enough to have low gravitational entropy. It was uneven enough to contain seeds. The fluctuations were small, but gravity is patient. An overdense region attracts slightly more matter. That added matter increases its attraction. The contrast grows. Dark matter halos form. Gas falls inward, shocks, cools, and fragments. Stars ignite. Heavy elements spread. Planets assemble. Every stage creates new channels for entropy. A star shines because its hot interior sends energy into colder space. A planet can support weather and life because it absorbs relatively concentrated energy from a star and radiates more diffuse infrared energy away. Local complexity grows while total entropy increases. Life does not violate the second law. It is one of the structures possible in a universe far from equilibrium, sustained by energy gradients that ultimately trace back to the low-entropy past. Black holes now dominate estimates of the observable universe's entropy budget. Supermassive black holes in galactic centers possess vastly more entropy than the stars and gas around them. In the semi-classical picture developed by Stephen Hawking, isolated black holes eventually evaporate through thermal radiation over timescales beyond ordinary imagination, adding still more entropy. A complete theory of quantum gravity may refine the final stages of that process. The long future may approach a state of dilute equilibrium in which useful energy gradients disappear. This is sometimes called heat death. The phrase sounds dramatic, but it describes an extraordinarily slow fading. Stars cease, remnants cool, black holes evaporate, and radiation stretches to immense wavelengths. That possible future is connected to the beginning by the arrow of entropy. A low-entropy universe can have a long story. A universe beginning near maximum entropy would have little capacity for organized change. There would be no substantial gradients to drive stars, chemistry, or memory. The existence of a history containing distinct eras is therefore tied to the special quietness of the first state we can infer. Cosmology usually asks why the universe has its matter content, expansion rate, and fluctuations. The entropy question asks something even more basic. Why was there room for anything to happen? We do not know, but we can observe the consequence. The microwave sky is smooth to 1 part in 100,000. Galaxies now fill a web of enormous contrast. Between those two images lies the irreversible unfolding of cosmic time. Let us return to the earliest picture one more time. Not to a point exploding in darkness, not to a finished universe compressed like an object inside a larger room. Instead, imagine a hot, expanding state present throughout every part of the region that would later become observable to us. There were no constellations, no horizon marked by stars, no distinction between a galaxy and the emptiness around it. Matter and radiation formed an almost uniform whole, interrupted only by tiny fluctuations. Those fluctuations were quiet, but they were not meaningless. They carried the future statistical pattern of structure. Given gravity, expansion, dark matter, and ordinary physics, they could grow. The path from that early simplicity to the present was not immediate. For fractions of a second, fields and particles followed rules at energies near the edge of tested knowledge. Within seconds, relic neutrinos began traveling almost freely. Within minutes, protons and neutrons formed the first light nuclei. For hundreds of thousands of years, the universe remained an opaque plasma. Then neutral atoms formed, and the microwave background began its long journey. Darkness followed. Gravity gathered gas into the first halos. Stars ignited and created the first new chemical elements since nucleosynthesis. Galaxies formed, merged, and changed. Black holes grew. The intergalactic hydrogen was ionized again. Billions of years later, one ordinary star formed in the outskirts of one spiral galaxy. Around it, a disk of dust and gas assembled into planets. On one of those planets, chemistry developed systems able to preserve information, reproduce, adapt, remember, and eventually measure the ancient radiation surrounding them. The connection is physical rather than poetic. Most hydrogen atoms in the human body contain protons that have survived since the first seconds of the hot universe. The carbon and oxygen were produced later in stars, but the protons from which their nuclei were built belong to the early cosmic inventory. The helium filling much of the universe was created before any star shone. The microwave photons passing through the room have traveled since the universe became transparent. They are faint and invisible to human eyes, but an antenna can receive them from every direction. The cosmic neutrino background should be passing through as well, carrying information from an even earlier second, though no instrument has yet isolated those relic neutrinos directly. The beginning is not merely behind us. Its remnants are present. Expansion continues to stretch light. Primordial helium remains in stars and gas. The acoustic scale remains imprinted in galaxy clustering. The first density fluctuations remain expressed in the cosmic web. Every observation of these relics is a conversation between the present and an earlier universe. Future instruments will make that conversation more precise. New CMB observatories will map polarization and gravitational lensing, searching for primordial gravitational waves and additional light particles. Improved measurements of the microwave spectrum may detect tiny distortions created by energy release in epochs that ordinary images cannot reach. Galaxy surveys will measure baryon acoustic oscillations across larger volumes and test whether dark energy is constant. Gravitational wave detectors may observe backgrounds from early phase transitions, cosmic strings, or inflation, though separating primordial signals from astrophysical sources will be difficult. Radio arrays will continue searching for the 21-centimeter landscape of cosmic dawn. A successful detection could reveal when the first stars heated the gas, how reionization spread, and whether dark matter behaved exactly as the standard cold model predicts. The James Webb Space Telescope will continue finding and characterizing early galaxies, while future observatories will survey wider areas and discover rarer systems. The earliest known galaxy record will change. The more important result will be a population from which the history of star formation and chemical enrichment can be reconstructed. Particle experiments will test neutrino properties, dark matter candidates, CP violation, and rare processes connected to baryogenesis. A discovery in a laboratory on Earth could alter our description of the first second. Precision may also reveal that some current tension was caused by calibration rather than new physics. That outcome would still improve the model. Science advances both when a new ingredient is found and when an apparent anomaly is understood. No future observation is likely to provide a simple photograph labeled moment zero. The earliest boundary may remain indirect. We may learn about it through statistical patterns, relic backgrounds, and constraints on theories rather than through an image. That does not make the knowledge less real. No one has watched a proton's entire history, yet its properties can be measured. No one has traveled through the interior of the sun, yet neutrinos and oscillations reveal its structure. In cosmology, the surviving evidence is sparse in some ways and abundant in others. The universe has preserved a thermal spectrum more perfect than almost any laboratory source. It has preserved nuclear abundances from its first minutes. It has preserved sound waves as patterns in both radiation and galaxies. It has preserved the growth of structure across cosmic time. From those traces, a coherent history emerges. The history does not answer why reality exists. It does not prove what, if anything, preceded the hot expanding phase. It does not reveal the identity of most matter or the nature of the energy driving acceleration. It does not yet explain why the beginning possessed such low gravitational entropy. But it tells us that the present cosmos was once radically simpler. Everything visible was once part of a hot plasma without atoms. Every galaxy grew from variations too small for the eye to notice on a microwave map. Every heavy element appeared only after stars began transforming the original hydrogen and helium. Complexity was not placed into the universe in finished form. It accumulated through time. That may be the quietest meaning of the Big Bang. The beginning did not need to contain stars in miniature or galaxies waiting to unfold. It contained physical relationships, energy, expansion, fields, particles, and slight differences from place to place. Gravity and time did the rest. Somewhere in the ancient plasma was the matter that would become the local group, although no boundaries separated it from neighboring regions. Within that broad region were the particles that would later pass through many stars, clouds, and perhaps living systems. Their futures were not written as individual paths. Quantum events, turbulent gas, stellar explosions, collisions, and biological history introduced contingency at every stage. Yet the possibility of those futures rested on the early conditions. We live at a time when the microwave background is still measurable, distant galaxies are still visible, and stars continue to shine. The universe is old enough to contain observers, but young enough to display much of its history. That is a temporary privilege. Far in the future, accelerated expansion may carry most galaxies beyond view. The microwave background will be stretched to wavelengths difficult to detect. Future astronomers confined to a merged local galaxy may have a much harder time reconstructing the hot Big Bang. We are able to see the evidence now. A dim microwave glow, a quarter of primordial helium, galaxies receding in a measured pattern, a web grown from tiny fluctuations. These are quiet signs. Together, they describe the earliest chapter we can read with confidence. Beyond that chapter lies a boundary where equations become uncertain and questions remain open. Science does not need to hide that boundary. The unknown is part of the map. The Big Bang is not a story made smaller by uncertainty. It is a story made honest by knowing where certainty ends. 13.8 billion years of expansion separate the early plasma from the present sky. Yet the distance in explanation is surprisingly short. A few physical principles connect them: gravity, quantum fields, thermodynamics, nuclear reactions, atomic transitions, and the changing geometry of space. The universe has spent almost 14 billion years turning small differences into structure. It began, as far back as our evidence can clearly reach, hot, dense, smooth, and quietly uneven. And from that quiet unevenness came everything we know. Good night.